strange thing to imagine space with something in it, because there's two different things, matter and space. So how do we get matter into space? I mentioned this already, singularity. What I'm going to do is start by constructing a reverse argument. I'm going to create an answer and then work out what the question is afterwards. So I'm going to look at a space containing singularities, what we call a multiply connected space. So we have a space containing a singularity here. We call that multiply connected. This is standard topology. And that's an open space simply connected. Now, if we perform a circuit around this, suppose we parallel transport a vector around this. So we parallel transport the vector so it's tangent to the edge of this circuit all the time. And we start, say, there, and it's pointing that way. When we arrive back at the original point, it's still pointing in that direction. However, if we should do it around the multiply connected space, what will happen is that the vector, once we've gone around the circuit, will end up pointing back in the opposite direction. That's not physics, that's mathematics. The singularity in the right hand space. So it's very safe. Oh, well, there isn't. No, but I'm saying that we don't need to make any physics assumptions to do that. It's a mathematical argument. But there isn't. They are totally connected. They're not separate. So the double circuit provides us with a direct analogy with a fermion with spin half. So you can imagine that there is in fact a fermion. And it is its own multiply connected space. It doesn't need any space around it to perform this trick, because that's exactly what a fermion does. It has to go around twice to get back where it started. And we call that spin half. And as we know, if we bring physics into it now, in the case of the fermion, this connects with the bit of the radon. The switching, if you've got fermion, you've got four wave functions in a fermion, two of which are states, two of which are anti-states, and it switches continue between them. And which is also interpreted as switching between real space and vacuum. So the fermion in and out of vacuum all the time. Now, if we look at the fermion algebra, the Dirac algebra, mathematically, the gamma matrices, the things that go into the Dirac equation for the fermion, the algebra that's needed, what we require is a commutative combination of two vector spaces, and we will show that in a moment. So that's interesting that the fermion should have this property of requiring a double circuit, and it should also mathematically require two vector spaces to specify it. So it's a logical conclusion to put the two together to say that in some way there are two spaces, and that the fermion needs to go around twice because it's got to go around two spaces at once. It spends half its time in one space and half its time in the other, and that's why it requires a double circuit. And because the fermion is a physical singularity, one can imagine that this is what is required to construct a physical singularity in space. For example, at fundamental particle fermion, we require to put two spaces together in some way. The mathematical two spaces. So here we need a little bit of algebra, a standard algebra. This is the quaternion algebra, and these are the quaternion units follow this algebra. There's anti-commutative, and the cyclic, and they have norm at -1, square to -1. Now, what we want to do now is complexify that. If we complexify that by instead of, so we complexify the quaternions, so we multiply them by the ordinary square root of -1. So I times quaternion I becomes this new symbol here. We get what we call, in various terms, geometrical algebra, Clifford algebra, and also multivariate algebra. complexified quaternion algebra, we get I squared j squared equals k squared equals minus I times ijk equals 1. And the important thing is that ij equals minus ji, same as quaternion, but this time it doesn't equal k, it equals this pseudo-scalar I times k. And we find that this algebra is also isomorphic to power matrices. And if we imagine complexifying that algebra, we go back to quaternions. So each is the complexified version of the other. And the vectors in this algebra have what we call a full product. It's a combination of, that should be A, not I. That's a times A dot B, and that's I A cross B, A dot B. So we have a dot product and a cross product combination. And then all the rules that we just mentioned can be derived in that way from that. And these terms we call pseudo vectors, and we're very familiar with them in physics. We also call them axial vectors, area angular momentum, and I is the pseudo-scalar for example volume. And so if we now put all the elements of the vector algebra together, this is the basic algebra, and these are the three sub-algebras that it contains. This is the bivector algebra, which is the same as quaternion algebra, also known as pseudo-vector, and I is also called trivector or pseudo-scalar. And so the complete algebra is described by this. Now imagine another algebra exactly the same. This time I'm going to use blue instead of red. So this is a dual vector space, exactly the same structure. And now we already done that. Now we put them together. If we put those two algebras together by commutative multiplication, the tensor product, then what we get is that, well, it's plus and minus values of that. We get plus values and minus values of all these. These are all possible results of that. And in total, you can see there are 32 there, there are 64 in total. And we could do it in several ways. That's using dual vectors, two vector spaces. But we can also do it using complexified double quaternions, because vectors are complexified quaternions, so we just have complexification here. And so this is a vector quaternion algebra, one set of vectors and one set of quaternions. We can get the same algebra with that. Or we can use complexified double quaternions, so again we get the same algebra. So those are completely isomorphic to each other. Recognizable as the algebra of the Dirac equation or the gamma matrices, because the gamma matrices, the 5 gamma matrices, multiplied out in every conceivable way will produce 64 elements exactly the same as those in their behavior. So another way of doing this is to take two lots of sigma matrices and take a commutative combination of those. If you make a commutative combination of those, 2 by 2 matrices, you get all the 4 by 4 matrices of the Dirac algebra. So, in every sense, the use of the Dirac algebra can If I do that, I will always get the same structure of the generators. So let's see. If I do that, it will always look something like this. One of the vector units, let's take this one, the blue one, retains its symmetry. It retains its rotation symmetry. You see that the I, J, and K are each connected to the same object. So the I, J, and K still have their rotation symmetry. They're not changed in character by being associated with something different. They're associated with one object. However, the red unit, which is the other vector algebra, are represented as quaternions, but they can also be represented as vectors like that. This other one, its symmetry is broken. Because you see the red K and the red I are associated with something different, and also the red J. The three red units are associated with something different, and so their symmetry is broken. So the price of creating the minimum number of generators is to break the symmetry. And ultimately, this is responsible for the symmetry breaking in fundamental physics. Because this one here, one can ultimately show creates an SU3 symmetry, those three. This one here creates a, it actually should be the other way around. I normally choose the pseudo-scalar I to go in front of the K. And that one becomes the SU2 symmetry. I don't have that I there, the black I. And I have the red and blue in that. And that becomes the SU3. And this one doesn't have the I there, and that one is the U1 symmetry. Ultimately, that's the reason for that symmetry breaking. The fact that you stick two lots of vectors together, and if you do that, one of them loses its symmetry, the other one retains it. So it's a hidden symmetry and it's a broken symmetry. And whichever way you do 5 generators, it always has that pattern. Always has that pattern. Now, physically, the physical meaning of this, see, that's the way I prefer to write it. The physical meaning of this is that this one becomes the energy operator, this one becomes the momentum operator, and this one becomes the rest mass operator. And these E, Px, and Py, and M are simply scalar coefficients. That they are not the reason why that is energy. The reason why that is energy is in that algebraic structure. This is just a scalar coefficient. Because we're familiar with it as energy, we just use an E for it. But that's only a scalar. The real meaning of it is in that algebra. So the characteristics of physical determinants are determined by the algebraic operators, not the coefficients. And now, what we see is when we put this together, this is the complete set of generators for the algebra written in that form with scalar coefficients. And when you multiply that by itself, you get 0. Because I can collect the 3 momentum terms into one momentum operator, that will be more convenient later. We simply get Einstein's energy momentum equation, simply by multiplying them together. And this object here becomes the square root of 0, a non-zero object. And this object, mathematically we call it a nilpotent. Wolfie used the word nilpotent yesterday, so this is a particular kind of nilpotent, one that squares to 0. So that squaring to 0 actually makes the two spaces four wave functions. Here you've not got four wave functions, you've just got four variations on the same one. Of course, the Fermion doesn't have to be pre-installed. We can replace E, not by D by dt, but we can add field terms as many as you want. You can add an infinite number of them. It doesn't matter how many you add. What we'll find is that we can still define the operator in this form, so that E becomes this, or the P becomes that. But the phase term won't any longer be that. It won't any longer be the simple exponential. It'll be whatever you need to create an amplitude with this general structure, which squares to zero. So once you've defined your operator, then that's it. You don't need anything else. It creates its own phase, it creates its own amplitude, which squares to zero. So the operator statement tells you everything. There's no need for an equation at all. So to do relativistic quantum mechanics and quantum field theory, for a Fermion n space subject to any number of interactions, we simply define an operator in that form. And then what we find is that the operator acting on phase factor, which there's only one phase factor it can operate to do this. Once you define the operator, squared equals amplitude squared equals zero, and that's it. So we don't need an equation as such. And it also gives us a formal way of separating the local from the non-local. So the bracketed term, whatever is in that bracket, represents the Fermion creation operator or wave function, and determines how you get conservation of energy for that Fermion. And of course it has to be, it's an open system, in actually interacting with the rest of the universe. And it's local, and it's got the Lorentzian structure which requires that that's built in from the beginning. However, if you add or multiply nilpotent wave functions, if you add or multiply these brackets, then that is no longer a local operation, that's a non-local operation. That's superposition, combination, all those things, they don't require a Lorentzian structure. So whatever's inside the bracket is local, anything outside it is non-local. Now, let's have a look at this nilpotent structure. By multiplying that by itself equals square to zero, and we can say that two identical fermions, the combination state is zero. So that's one way of looking at Pauli exclusion. So that's the way we could look at it. That multiplied by itself is zero, so two fermions can't be the same. Alternatively, we can take antisymmetric wave functions, which is the standard way of doing it, and this is how I would do psi 1, psi 2 minus psi 2. It would look something like that. The interesting thing here is that this tells us something else. It tells us that the only information that exists that's independent to a particular fermion is the direction of the instantaneous direction of the spin vector. In fact, everything in that fermion is in that. All the information is somehow in that. I think this relates to Wolf's projective geometry, because another way you can look at it is by thinking of it in terms of projective geometry, that all the planes of all fermions intersect. And that's Pauli exclusion. That you get, these create there's a plane perpendicular to each of these, P1 and P2, these two fermions, and the plane must intersect. All the planes must intersect. The same place? No, not the same place, but they must intersect somewhere. You can't have parallel planes. They're non-parallel. So, of course, we see the standard result there. And I say this is quite remarkable because that's all the only thing that differentiates fermion from another. So, in other words, all the information is in that direction. Not even in the magnitude, in the direction of that key thing. Amazing. Okay. So, we see the nilpotent condition is defined in two different spaces. We can either have the axes Ki and J in red, or we can have the axes I, J, K in blue. The order of these is just arbitrary, so I wouldn't worry about that aspect. So in the real space, the vector P has all the information. So this is the real space, P vector carries all the information. In the other space, so this is the blue space, P must have a unique direction. But if we take the red space, these Ki and J, then EP and M must be unique. non-local. And we can also see it as a way of defining the universe to be totally zero. So I think this algebraic structure tells us the universe is totality zero. As does the Dirac equation, really, if we read it properly. So let's imagine what this means. We create a fermion with this wave function from absolutely nothing. So what do we do? We pluck it out of nothing, and this can have potentials and stuff. It doesn't have to be a free fermion, some sort of fermion. And then we have to then negate that by creating a vacuum which is exactly its mirror image. And that vacuum must represent everything else in the universe that makes that fermion state possible. So in other words, the rest of the universe. So F is the fermion, V is the rest of the universe, and it must add up to nothing, it must multiply to nothing.
Zero is nothing.
Well,
No.
alright,
Never.
well, whichever. But I think it is nothing in this case. Mathematical zero is nothing, but this zero is nothing. Yeah, I agree that mathematical zero is nothing. 2 minus 2 isn't nothing. But this zero is nothing. It's just that we can never quite represent it.
You see,
Yeah, I've got to continue, otherwise I won't finish. So, say, creating a singularity immediately creates a hole in nothing, which we call vacuum. So we create the sink and source simultaneously. And again, that's another way of describing power exclusion. We can say that no two fermions have the same vacuum. Right, and say the object created, described by the Dirac equation is a singularity. I'm saying that to create the singularity state, we need two vector spaces, but nothing else. We don't need any other information. That is the total information we need. And it's not really two sets of information, it's one. The second space in creating a zero totality acts as a kind of anti-space. So if you want to create nothing, a whole, a singularity, then whatever you want to call it, then you've got to negate what you've got in the space. So negative energy, in my view, represents vacuum rather than localized continuous state. And I have used various terminologies for this, but I'll leave that for the moment. I don't know how much of this I'm going to manage to get to, but let's just mention one or two things. In the standard structure, the observed particle state is the first, so we've got 4 states in the column. What are the other 3? The other 3 are in effect P, T, and C transformations of that first state. So you've got the initial state, and P, T, and C transformations. Also, and again, I'm sorry, you have to look at that. U is minus plus. We have 3 bosonic states, which are effectively the fermion and its appropriate antifermion, or fermion and fermion. One of the interesting things is that the spin for what 0 boson cannot be massless. Hence why the goldstone boson must become a Higgs boson. Another way you can look at it is to say that the fermion and antifermion cannot both be left-handed. One of them, the blue one is correct, the red one is incorrect, or vice versa. Only one can be true. We can also separate out 3 components, and if we highlight one of these at a time, we will get something that is very much the SU3 symmetry for the strong interaction. Also, another interesting thing is that you can, this is an idempotent multiplied by itself to produce itself. I can multiply the fermion by any number of idempotents of that kind, and it won't change. Or J, or I. And the interesting thing there is that these are like kind of vacuum components, but it's like to split the continuous vacuum into 3 components along these 3 axes. So that's the meaning of that little space. They have they correspond to respective transformations of those. In principle, they're associated with each P and M, and they split the continuous vacuum into 3 discrete units. Effectively, this is what we can understand the meaning of charge to be. And originally, when it came at this way of me if you like. And if one of this property, which I've not do today because we don't have time, you can show that the structure actually incorporates the fundamental interactions. And the interesting thing about these interactions is that they are purely results of spherical symmetry. SU2, SU3, U1 are spherical symmetry groups, really. So this idea that you can put them all together and change spaces as a result is incorrect. You can certainly embed them in a higher space, but you can't recreate space to see this. I won't go into that. Yeah. One of the things I did find out is that, well, essentially, that these things are connected with the angular momentum. They're separately conserved aspects of angular momentum. And the conservation of angular momentum is actually three laws, not one. I think you need three different laws with three different symmetries to explain it. So this is the partitioning of the vacuum. Another interesting thing here is that if I do k on either side, that one becomes minus, that one stays the same, next one's minus. So in other words, the fermion, because all this is just that fermion structure, is also its own boson in the vacuum. And that has consequences for renormalization and so forth. I don't believe that. These are different terms of use. Vacuum space, the three axes represent the partition of the vacuum. Charge space, ultimately you can pin it down to these three symmetries of the interactions. Anti-space, that is the dual, and effectively zeroing the space you start with. Just want to mention one or two things here. We've seen this, that you can, the two spaces do both do Pal exclusion. They can also both do spin half. Because you can get spin half from the anti-commuting part of P, which you use in the blue space, or you can get it from the Thomas precession, which is relativity, and relativity is represented by the red space. You can do this, I've seen this done. I've lost the addition law from two dimensions of space, so that's using that one, or you can use it using relativistic space-time. Or you can do the holographic principle of two spatial coordinates or space and time coordinates. Now, why do we only see one space? Well, because only one of the spaces is actually truly a physical quantity. The other space, mathematically, is a space, but it's not physically a space because it's made of three different quantities. It's made of a scalar quantity, a pseudo-scalar quantity, and a bivector quantity. In other words, there's all the other information that isn't space bundled together. And that's why it looks mathematically like a space. It isn't space at all. You can see you bundle these three things together, and they have the same properties as a space, but obviously they're not one quantity. And that's why we don't observe it. Okay, I think we've established all that. And that's it. Thank you.
Finding the generating set and seeing that one part collects up as a vector and there seem to be two scalars. What in your intuition at that stage, imagining that you were coming up from nearly nothing, would suggest to you that one of the scalars should be a mass and the other should be energy?
Well, that is simply from what I've seen.
I know already from the top down.
From the top down.
Right thing for it to be wrong.
Well, the other one, the energy one, also relates to time. Whereas the mass one doesn't relate to time, it only relates to mass. So that's why one should be an energy and one should be a mass. Because energy is also a time-related quantity, which mass is pure discrete masses. And also the energy really is a continuous quantity, whereas the discrete mass is a discrete quantity. And they are different in that respect.
When you use the term random local, how is it related to Einstein's use of the interaction on the exterior of the wave?
Yeah, well, that's what it does. Because power exclusion is the whole universe immediately. It's got nothing to do with the light cone at all. And all such non-local things, superposition space and so on, are non-local in that way. non-local and local ultimately, because you cannot describe the system without doing both at once.
That it seems to me to be an entirely different use of the word.
I don't think it is. It's just more subtle because I don't think non-local is separate from local. I think they're just aspects of the same thing.
Well, that's Einstein certainly.
No, well, Einstein wasn't right about locality in my view.
I think this is, I think it's something that's having Albert, we want to
Now, with gravity, it's something I didn't mention because it's another complication. Is that gravity essentially is negative energy. And people have long recognized that gravity is negative energy. Now, negative energy in this system corresponds to vacuum. And I've always believed that gravity was really a vacuum thing. And that if you look at if string theory and in other things, and all in my own work, that gravity is like a kind of summation of everything else. It's like a summation of all the other forces and all the other interactions.
Could you say similarity?
I'm not sure. I have to think about that. But gravity is, the gravity gauge theory correspondence is now becoming standard in string theory. But I've always had it. That gravity is a kind of summation of the rest. With regard to things like dark energy and so on, I think this is the reason why you've got this disparity of 10 to the 122 order of magnitude thing wrong. Because people keep thinking of gravity as being a local force when it's not nothing at the time. It's like all of the others put together, but it could not be local.
A consequence.
Yes.
Peter, how do you get 64 elements from 5 generators? 5
So 10 to the power of 5 is 32, plus or minus.
or 5 from like 2.
Yes, because you do it both ways, and it's not like it is two. So that's how you get 32. It's the same way you get with the gamma matrices.
They have associated space.
Yes, indeed.
With extension.
Yes.
In the 3 dimensions.
Yes.
So, how does space and anti-space relate to the extension in your conception?
Well, space is extension, and the rest is the dual to it. That you need. To have no extension, that is singularity. You see what I mean?
How about anti-space?
The anti-space is everything else other than space. But in some way, the universe has to create zero, totality. And the counter to the space, which is the only thing we observe, is everything else put together, and that's what we call the anti-space. And that's why one gets points of singularity.
Time for another question.
You mean time as well, and that's without expansion.
Yes.
The initial question is, what about time?
What about
Time.
anti-time? Well, you get that in the Dirac equation because you get d by dt minus d by dt. When you add them all up, you get zero. So there is time going in the opposite direction, but it applies only in vacuum. So that's why we have no more matter than antimatter. They're the same amount. One's in space and the other's in vacuum. Yeah, and same with time.
If there's no more questions, then